In this problem, we consider the scenario of a titration buret. That's one of those tall, thin cylinders used in chemistry to gradually add fluids to a mixture. The physics behind that process is there's water in the container and there's a force of gravity, so there's some potential energy, and it's not that complicated to work through the physics and arrive at this conclusion. The height of the water in the buret is dropping because of gravity, but more directly for our differential equation applications, we can find out the rate at which it's dropping, and that rate is proportional to the square root of the current water height. As we saw back in week 1, we can easily translate that kind of statement into a mathematical statement, which will be a differential equation. If we let h be the height of the water in the buret, then the rate at which the water height is changing would be dh dt, is proportional to, is equal to a constant times, and what is it proportional to? It's proportional to the square root of the current water height. So this is another illustration of that simple relationship between a mathematical statement in words here and its mathematical interpretation as a differential equation. We note specifically how simple the differential equation is, but we also note that what we really would like to have is h equals. We'd like to know what the height is going to be at any point in time. That is not given by this differential equation, but only by its solution once we have that. Before we move towards that solution, though, there's some important notes that are relevant to looking at this differential equation. In particular, the constant of proportionality here, that k, its sign is quite important because we know that the sign of derivatives are very important, and the k is really what's going to dictate that sign of the derivative. So what we note is dh dt. Thinking back to derivatives, we know that h is decreasing because it's the height of water in this buret, and so the derivative of h with time has to be negative. We also note that square root of h is positive by definition. Whenever we need a negative square root, we put an explicit negative sign out front. And if we look at the ingredients in our differential equation, we want our derivative to be negative. We know that this square root of h term is positive, so the only way for that to work out is k must be negative. Otherwise, we would have a much less realistic physics application where the buret would be filling up with water over time, which would be a little unusual. Another important starting process we can look at even before we get a solution is to identify some interesting points in the solution itself. At what height h does the water level become constant? This kind of question is relevant for a lot of other scenarios too, concentrations, populations. We're interested when things settle down. And again, one nice thing about differential equation models is if we say we're interested when our variable is constant, well, that immediately leads to an alternative statement, which is that its derivative is going to be equal to 0. And we started with a differential equation with a derivative in it. So if we want h equal to 0, h equal to a constant, then that's equivalent to saying its derivative is 0, or saying that 0 equals k root h, and that means k equals 0. Well, that's going to be impossible from the physics. If we had that, then the water level would never drop. Or it means root h equals 0, or h equals 0, and that makes complete sense, because what constant value leads to no change? Well, that has to be an empty tank. An empty buret leads to h equals 0, which will lead to dh dt equaling 0, which will lead to h being constant. So once the buret is empty, it stays empty, is the translation of that mathematical statement. So this is a nice confirmation that our model makes some kind of sense. We'll now move on to actually finding the solution in the general case. Our differential equation was dh dt is k root h, and we notice this is first order, What we also have to notice here, lest we fall into a rut, is that this is non-linear. We have the square root of h. It's not h by itself combined with some t's. It has a square root in the h, and this is not linear, and that means the only technique we can use will be separation of variables. So that's important to note, because one of the challenges in this class is to be able to identify the type of differential equation so that we can apply the correct solution technique or the appropriate solution technique. Having done that here, we can recognize, okay, it is separable. Let's go ahead and follow that process then. We're going to separate and integrate. We bring the dt up. We'll leave the k on the right-hand side. We'll take this root h and bring it down. And then we'll integrate both sides. Before we do that, we'll convert this to a power to make it easier to integrate. It's in the denominator, so negative, and it's a square root, so a power of 1/2. Then we can proceed to integrating the left-hand side. Add 1 to the power. Negative 1/2 plus 1 is positive 1/2. Divide by the new power. On the right-hand side, we get kt, and after both integrals, we need a plus c over all. And then we simply solve for h, because that's the unknown height of the water in our buret. So we'll bring the half up. We have square root of h is equal to 1/2 kt plus 1/2 c, and h then is going to equal 1/2 kt plus 1/2 c all squared. And that is our general solution. And we can see that this has some kind of parabolic shape to it. And so just as a rough sketch, what we'd expect to have happen is a curve like this where the height is plotted against time, and we expect to have it start at some point, run out most quickly at the beginning, and then eventually end up exactly empty, not like an exponential. There would actually be a terminus point here. And that's a pretty reasonable prediction over what time frame the water will flow out of a buret. Let's make this a little more concrete with some specific numbers here. The buret starts with water at 16 centimeters of depth. So at t equals 0, h equals 16. We can use that information to inform our general solution, which was h equals 1/2 kt plus 1/2 c. I'll write it as c over 2 squared, except the t here is also going to be known. The t is 0. So we can plug that in, and then we get 16 equals c over 2 squared. That leads us to 4 equals c over 2. And we note that what we actually want is c over 2, so let's just stop there and see how that works out. Notice there is another alternative. We could have c equals -4, c over 2 equals -4. However, we already know the kind of solution we're looking for. We're looking for a solution that goes down and down and down and then has a root when we graph height against time. And the only way for that to work is to have this value positive and the kt part here. We already know that k is negative. So we'd have a positive minus a negative inside, so the root would happen at a nice positive t value. That's not going to happen with a c equals -4. So, or c over 2 equals -4. So we can safely dismiss that based on the physics and the scenario and work just with this value here. So our new solution, our new updated solution taking into account the starting value of the depth is 1/2 kt plus c over 2, but c over 2 is 4. Next, after 10 seconds, so at t equals 10, the water level has dropped to a height of 4 centimeters. So h equals 4. We can take that and put that information into our solution again, and h is 4, so there's our 4, equals 1/2 k, t is now 10, and plus 4 again here. Now the only value left undetermined is k, so we can use this information to solve for k. We'll take the root of both sides and get, when we're done here, we'll have 5k's plus 4. We bring the 4 over, we get -2 equals 5k, k equals -2/5, and it's a confirmation of our earlier analysis that said k had to be negative. K is negative, check. And that then gives us the final solution with all the ingredients built in. We've got 1/2 times -2/5 times t plus 4 squared. That is our updated solution. We can cancel the 2's here if we like. Careful not to lose the negative though. And last but not least, we can use that to determine the time at which the buret will be empty. The buret will be empty when h is equal to 0, which means that 0 would equal our -1/5 t plus 4 all squared, and we simply solve for t now. Squared doesn't matter, we'll take the square root of both sides, and we'll end up with 4 equals 1/5 t, and at the end of the day, t equals 20 seconds is when the buret will be empty. And we can take a look at a parabola and see if that makes any sense at all. If this was 16 at the top, and it was down to 4 after about 10 seconds, to be empty after 20, doesn't seem unreasonable anyway. It certainly fits with the general trend that we'd expect from this kind of solution. The key thing, again, is just to note the processes. When we are given some values, those values will let us solve for unknown constants, be they the integration constant c or some kind of proportionality constant k, and we just work through and use that information as best we can to update and refine the general solution down to a particular solution that applies to our scenario.